All right, today we're going to talk about wave interactions. I'm going to read through this with you. We're going to talk about, highlight some vocabulary words. I'm talking about what they mean, how they relate. This will be in your Google Docs, this reading, so you can read along with me. Please answer the questions as we move along. They will be entered into your Edpuzzle. Answer those as we move along. And this is the last section on the introduction of waves. I'll have a brief little quiz for you tomorrow. So do that to the best of your ability. Today what we're going to talk about is how do waves interact with objects and how do waves behave when they move between two media and how do waves interact with each other. The first thing we're going to talk about is why do waves reflect? So we're talking about reflection here. A reflection occurs when a wave bounces back after it hits a barrier. All waves can be reflected. Light waves reflect off an object, allowing you to see the object. For example, light waves from the sun reflecting off the moon allow you to see the moon. Sound wave can also be reflected, and sound waves reflected off a barrier are also called an echo. So when you're standing on a tall area and you yell and you can hear it come back, that's the sound waves being reflected back off of the mountain. Okay, the waves in this photograph were formed by drops of water that fell into a container of water. When the waves caused by the drops of the water hit one side of the container, they reflect off. The shape of the reflected wave is the opposite that of the waves that struck the side of the tank. You can see that it's the opposite of that. Waves are not always reflected when they hit a barrier. Sometimes they pass through a substance. When a wave passes through a substance, it is transmitted. Light waves transmit through glass windows, allow light to enter a room. Light waves transmitted through eyeglasses allow the wearer to see them. So when we take a look at reflection, we're talking about waves hitting something and coming back. So let's take a look at the critical thinking here. How does your reflection in the bathroom mirror look when you raise your right arm? So when you raise your right arm, what happens? Okay, what happens when you raise your right arm? It's kind of the same thing as like when you're videotaping here. When I raise my right arm, what happens to that? Answer that question right now. Okay, the next thing we're going to talk about is diffraction. Why do waves diffract? Well, first of all, we need to understand what diffraction is. Diffraction is the bending of waves around a barrier or an opening. So the bending of waves. So you could think of light. Does light refract very well? Okay, if you have a light and you go around the corners, it's still light. Can you still see the light? I mean, does the light go around that? We'll talk about that a little bit, like sound waves diffracting. Diffracting is the bending of waves around a barrier or through an opening. Waves usually travel in a straight line. When a wave reaches the edge of an object or an opening in a barrier, it may curve or bend. The amount of diffraction of the wave depends on its wavelength and size of the barrier opening. It's important that you remember that. The amount of diffraction of the wave depends on its wavelength. Things with slow wavelengths are like sound waves. Things that have a really tight wavelength, have lots of waves. Those are things like light, microwaves, things like that. Sound waves are relatively long. You can hear voices from one classroom diffract through the opening of a door into the next other classroom. So when we're teaching and you can hear Mr. Shetka's TV or you can hear my TV when we're in the other classroom, that's because those waves, those sound waves are diffracting through the opening. Sometimes they'll even get louder. So the waves will be amplified, it'll amplify some of those waves so the waves will get bigger. Light waves are relatively short. You cannot see who is speaking in the classroom, but you can hear them. So if we take a look at this barrier here, if a barrier or opening is larger than the wavelength of a wave, there is only a small amount of diffraction. Take a look at that first picture. It kind of looks about the same thing. If the barrier or opening is the same size or smaller than the wave approaching, the amount of diffraction is large. So you can see that down here. the waves are starting to change quite a bit. It changes the wave a lot, whereas this barrier, it kind of looks exactly the same. So in your reading check then, it says, what is diffraction? So go ahead and write that in there now. And then let's take a look at number 3. It says, describe. Suppose the opening in the lower figure was made larger. What would happen to the shape of the diffracted wave? So if we see how we kind of have this cone shape here, if we were to make this a little bit larger, what do you think would happen? Do you think it'd be more like a cone, or did it be more like this, more just kind of a rectangular diffraction of the wave? Okay, continuing, we're going to continue talking about refracting. Why do waves refract? For what reason? For what reason are the refraction? Well, let's talk about what refraction is. Refraction is the bending of a wave as the wave passes through one medium to another. Now, for example, different mediums have different speeds. So, like when light travels through a prism, we'll separate those barriers of light depending on the wavelength of light. Same thing with water. Like water has a different medium, so light travels at a different speed through that medium. The wave changes speed as it passes through from one material to the other. The change in speed causes the wavelength to change. The resulting wave bends and travels in a new direction. So if you take a look at this picture down here, as the light goes in, you can see that it breaks. Okay, that breaks. It slows the wave down so that it goes slower. Okay, so let's take a look at your reading check. It says, what happens to a wave because of refraction? Is it making it go faster, or is it slowing it down? It's kind of like when you throw something in the water, it hits the water, and then it goes a different direction because that wave slows it down. This light wave is refracted as it passes into a new medium. The light wave is passing from air into water. The wave is refracted because the speed of the wave changes. Now, when you put a pencil in a glass of water, you will see that it looks like the pencil is broken. It's because those light waves are refracting. So we're looking at it differently than what it actually is. Refraction of different colors. The light waves from the sun pass through a droplet of water in the air. The light is refracted. The different colors of light travel at different speeds through the drop. Therefore, the different colors are refracted by different amounts. The light is dispersed or spread out into separate colors. The result is a rainbow. Now, Roy G. Biv, red, orange, yellow, green, violet. Now, some of the colors we won't see so much, but here's the glass prism that I was talking about. When light goes into the prism, it slows down because it hits the medium and it refracts. And that's why we get these different colors. And the same thing happens when you see a rainbow. So when you're seeing a rainbow, what's happening is light is going through water vapor and it separates those different wavelengths into our Roy G. Biv, red, orange, yellow, green, and violet. That's what causes that rainbow to show up. So that's refraction that causes it. Look at reading check number 5. What does light do when it disperses? So what is light doing? Now, why do we get these different colors? Why is it red, yellow, green, violet? Why does it separate? Why do you think that happens? Why do you think we get that Roy G. Biv? Well, each one of these colors, red, yellow, green, and violet, have different wavelengths. And then when they pass through that medium, those wavelengths are slowing down or they're changed. And that's what separates this color. That separates our white light. White light is made of that Roy G. Biv. So in every single thing of white light, you have red wavelength, you have an orange wavelength, you have a yellow wavelength, you have a green, you have a blue, and you have an indigo, and you have a violet. Now, orange and indigo don't really show up, but they are in there, and sometimes you can see them a little bit easier. So that is why that happens. Okay, the last thing I want to talk about today is what is wave interference and what is a standing wave. So How does wave interference deal with the standing wave? As matter has volume, therefore objects cannot be in the same place at the same time. However, waves are not made up of matter, they are made up by energy. So more than one wave can be in the same space at the same time. Two waves can meet, share the same space, and pass through each other. When two or more waves meet and share the same space, they overlap. Interference is the combination of two or more waves to form a single wave. So, interference is the combination of two or more waves to form a single wave. So if you look at your reading check there, it says, what is the combination of two or more waves to form a single wave called? And that is called interference. Now, we have two types of interference. We have constructive and destructive interference. And you can kind of, when you look at those words, you can kind of see that constructive would mean to build up and destructive means to destroy or take away. So the first one we're going to talk about now is constructive interference. Constructive interference occurs when the crest of one wave overlaps with the crest of another wave or waves. The troughs of both waves will still overlap. The energy of the waves adds together to make a higher energy wave. The new wave has higher crests, deeper troughs, and therefore a higher amplitude. So it's getting louder or bigger. Okay, so it's like you're combining two things. You have one little wave and you put another wave together. If we can make those waves meet at the same time, we're going to raise the amplitude of that wave. If you take a look at the picture down there, the two waves approaching, when they hit each other, they make one giant wave, but then they continue on. So it's not going to continue to happen forever and ever. Constructive interference, with waves combined by constructive interference, the combined wave has a larger amplitude, which means it's a bigger trough, bigger crest. Take a look. Look at number 8 there. What does the medium do after the waves have overlapped and are continuing their movement? So what happens? Do they stay together or do they just continue? Now they just continue on, and we only get that one giant wave for that one time they're together. It may happen again in a series of time, but the energy is still going to continue to move in the way that it's going. Let's take a look at the next one, a destructive interference. Now, destructive interference occurs when the crests of one wave overlap with the troughs of another wave. The energy of the new wave is less than the energy of both waves. The new wave has a lower amplitude than the original wave. If the crest and the trough have the same amplitude and meet and cancel, there is no wave at all. So if you have the crest and the trough meet, so a high point and a low point, and they meet, it just cancels it. It doesn't even look like there's a wave there. Energy is still being passed through, but there is no wave. Now, in a real world demonstration to this, you would probably see this in your noise canceling headphones. So these new technologies that have come out for these noise canceling headphones, they send out a wave out of your headphone to deconstruct the other waves coming in. Now, some is going to get through because it might have such a high amplitude, so that your headphones are probably not going to be able to put out a wave the same size as that to cancel it out. But they can put a wave out there to minimize it or make it not as noisy. The last thing I want to talk about here is what is a standing wave, or how are standing waves created? In a standing wave, the patterns or vibrations make it appear as if the wave is standing still. A standing wave is called by interference between a wave and a reflected wave. For example, if you pluck a guitar string, the string makes a standing wave like the top wave shown in the figure below. So if we have constructive interference here, you can see that the waves are getting bigger, and then you have a destructive, which would cancel it out. It just looks like the string is going back and forth and back and forth. Remember, a standing wave only looks as if it's standing still. Waves are actually moving in two directions. Standing waves can be formed with transverse or longitudinal waves. You take a look at question 10. It says, what causes a standing wave? Now, what causes a standing wave? Well, it has destructive and constructive interference going back and forth and back and forth. A rope vibrating at certain frequencies can create a standing wave. The initial wave travels down the rope and will be reflected back when it reaches the end of the standing wave. Certain parts of the wave are always at the rest position. This point is caused by destructive interference between the waves. Constructive interference can be seen at the points in the waves where we have the larger amplitude. So if we look at this spot right here, that's our rest position, rest position, rest position. All right? So hopefully you guys understand standing waves, destructive and constructive interference. And that's going to do it for our last reading here. And this will be the introduction of waves will be over. So make sure you go back and look at this vocabulary words. Guys, make sure you keep these sheets and save them in your drive so that when you take the test, you can go back and look them over. All right? Have a good day. See ya.